Hello students, let's talk about doing conservation of momentum problems. So there's a few ways that we can do these problems, and we'll call this option number 2. So for any conservation of momentum problem, a collision problem, we want to draw a before and after picture and make sure that we're good with labeling everything with all the subscripts. When we have our before and after picture, remember that the total momentum of the system before has to be the same as after. So that's why we have these pictures drawn up. We're going to use P equals mv for each of the objects that we've drawn in our before and after picture. Be very careful of the subscripts. This is how we'll identify objects 1, 2, 3, if it's initial velocity, if it's final velocity. In addition, if it's an inelastic collision, there will be a shared common velocity. They'll be stuck together at some point in the before picture or in an after picture. So just make sure that you're aware of that and that your subscripts also reflect that common shared velocity. What we do then is we use P equals mv, and we'll have a set of mv's on the diagram, on the picture, and we'll use those mass times velocities that we've drawn to generate the equation. Once we have all that set up, we'll have an equation that is for the particular problem that we're trying to solve, and then we can find our unknown. So it's really not that complicated. Once we have that picture that's drawn up, I'm going to put a practice problem on the screen, and then I'll walk you, or actually two, and then I'll walk you through how to do those. Okay students, let's do a couple of conservation of momentum problems. So the first one, I have some bean bags, right, and they're sliding on some frictionless ice. So let's draw a before and after picture for this one. I'm going to see if I can squeeze everything on this one page. So we've got beanbag number 1. That's not going to be big enough. Beanbag number 1, we'll call this M1, is 3 kilograms. And this beanbag is moving along at 4 meters per second. And then there's a second beanbag. Call this one M2, and this one's slightly bigger at 4 kilograms, but it's not moving. So we'll say V2 is 0. And then they get joined together when they crash. So we have an after picture now. We've got M1 and M2, still 3 kilograms for the first one and 4 kilograms for the second one. And now they're moving with some shared final velocity, and that's what we're trying to find. So we know that momentum on this side has to equal momentum on that side, right? Initial momentum has to equal final momentum. So what we need to do then is we need to find what mass times velocity is for each of these by writing on our equation. So let me get rid of this. The way that I do that is I know that this has mass and velocity, mass and velocity, mass and velocity. So I'm going to write for the first one, M1 V1, plus the second one, M2 V2, that has to equal over here, M1 plus M2, they're joined together, times V final. So this is the equation that we'll solve for this problem, right? We've just generated that equation. If I got rid of some of the space that's in between it, I would just have M1 V1 plus M2 V2 equals M1 plus M2 times V final. Okay? To save a little bit of space on this page, I'm just going to get rid of this. We can see that it's exactly the same thing. And all we have to do now is we need to solve this equation over here for V final. But there is one other little trick that we can do. We notice that our second mass is not moving, so anything times 0 is just 0. So that means that this component actually goes away. So I'm left with M1 V1 on the left equals M1 plus M2 times V final on the right. And if I want to solve this for V final, I'll divide both sides by M1 plus M2, and I end up with M1 V1 over M1 plus M2. So this is the equation that solves our first problem. If we put all the numbers in, we've got 3 kilograms and we've got our 4 meters per second divided by our 3 kilograms plus our 4 kilograms. And then the calculator tells us that we get 1.7 meters per second. So that's the first problem. That's how we solve our conservation of momentum problem for number 1. The second one, which I am going to try to squeeze in over here, we'll see if we can make it work. There's an ice skater, and the ice skater is sliding along, we'll say on frictionless ice, and has a snowball, and then throws the snowball forward. And what we want to do is we want to find out, well, what is the velocity of that skater after the snowball is thrown? So again, we're going to draw our before and after picture. So on the before side, this is our ice skater, just doing a block. 62 kilograms is the ice skater's mass. And the ice skater is holding a snowball, which we'll call M2, and it's small, it's 0.2 kilograms. And they're both moving with a combined shared initial velocity of 2.5 meters per second. Then we have our after picture. And what happens now is, here's our ice skater, M1, still 62 kilograms. But now we want to find out what this V1 is equal to when the snowball gets thrown, M2, still 0.2 kilograms. The snowball gets thrown in this direction at 21 meters per second. That's a pretty good throw. Now we know that momentum on this side has to equal momentum on that side. And just like we did in the first one, where we found mv for each of the objects, we're going to do the same thing down here. Just to save some space, I'm going to get rid of this. So over here, what have I got? I've got m1 plus m2, and there's a shared common velocity, which is the initial velocity. That must be equal to m1 v1 plus m2 v2. So we have the same setup as before. Now, up here on the first one, we could get rid of this because this one wasn't moving. We don't have that luxury down here. Everything is moving the whole time. And so now what I have to do is I have to take this equation here and I have to solve this for v1. So I am going to rewrite this one because it's kind of stretched out, just to make it a little bit easier to see. m1 plus m2 times v initial equals m1 v1 plus m2 v2. Okay, and what we're trying to do is we're trying to solve this for v1. We have to solve it for this. So the way that I'm going to do that is I'm going to subtract m2 v2 from both sides. So I'll have m1 plus m2 times v initial minus m2 v2 equals m1 v1. And now all I have to do to get v1 all by itself is just divide by m1. I'm going to rewrite it this way for the equation. So v1 equals, I've got m1 plus m2 times v initial minus m2 v2 divided by m1. So this equation, which clearly is not on a formula sheet, we derived it using conservation of momentum, right? All we had to do is use P equals mv for each of the objects, recognize that momentum before has to be the same as momentum after to get our equation. Once we have this, we just put the numbers in. So we've got our 62 kilograms plus our 0.2 kilograms. Our initial speed was 2.5 meters per second minus mass 2 is the snowball, 0.2 kilograms, thrown at 21 meters per second. All of this is divided by the mass of the skater, which is 62 kilograms. And the calculator does all the work. Now remember, we started off moving at 2.5 meters per second, whipped that snowball in front of us, gave the snowball a little bit of that forward momentum. which means that we cannot have as much momentum, and we can see that our velocity dropped from 2.5 to a whopping 2.4 meters per second. Seems like a lot of work just to go a tenth of a meter per second less. Okay, so that's how we do it. We generate our equation using P equals mv, momentum before equals momentum after. Give the rest of those a try, and I will see you in class.